Hello, welcome to the Tech Talk. And today we are very happy to invite the old friend of Pinterest, Juba, to come and introduce his new technology, especially on the data infra, and to give you guys a quick overview of who Juba is. He is the co-founder and the CTO at Rockset, a company building software to enable data-powered applications. And before that, he is the founding engineer of RocksDB, where we use in Pinterest a lot, and the founding engineer of HDFS. And before that, Juba has a lot of experience, such as early contributor to VXFS at Veritas Sandpoint Direct Storage System, was the co-founder of OneReceipt.com, an e-commerce startup based in Sunnyvale, and was the senior engineer of IBM Transact Labs. So a lot of experience, and we are so happy to welcome Juba here. So yeah.
Thanks a lot.
Yeah, you start.
Thanks a lot.
Yeah, okay.
That was like a long introduction. I forgot a lot of stuff that you kind of spoke about me. So thank you. It's really good to be back here at Pinterest. I came here a couple of times earlier because I had a lot of friends, and even now I think I know quite a bit of people in the audience. So it's always fun to be here. I think today I'm going to focus on the technology behind Rockset. I'm going to talk less about what Rockset is used for and other stuff. So I am hoping that it's a technology that interests you. And please ask me questions if something is not very clear. So just a short introduction about myself. So I have been at Rockset now for the last 2 years, building data infrastructure as a service. Before that, I worked at Facebook for a long time. I built the RocksDB database along with many other people in the team. And also I worked on many other Facebook products. And before Facebook, I was at Yahoo. I built the early versions, or like the 0.1 version of the Hadoop file system in the very early days, before, when the team was probably like 3 people or so. I still remember the first intern at Yahoo who was using the Hadoop file system and trying to do junk shell, if you remember him, right? So those are very, very early days at Yahoo. I also built I also am a code committer to HBase because at Facebook we used to use HBase in a big way like 10 years back for Facebook chat application, which was kind of the granddaddy of Facebook Messenger. So today I'm going to talk about a database that we are building at Rockset. And sometimes people ask me, hey, why do you start building yet another database? There are hundreds of databases out there, and it's already, the situation is quite confusing to people to figure out what to use and what not to use, right? So the focus for me was, how can you make it easy for people to use a database or a data platform, and you can get value out of your data very quickly rather than trying to do a lot of stuff yourself. Like companies like Pinterest or Facebook are different because I think they can hire a lot of great people to do a lot of challenging work, but most people in the enterprise can't afford to do that, right? So Rockset is essentially optimized for people efficiency rather than hardware efficiency. Like if you look at every open source database, they're mostly optimized for efficiency, or like hardware. How can you use less amount of resources and do more work? Whereas for Rockset, the whole design goal is, how can I make people use data very quickly? So you'd see how our architecture is slightly different compared to other systems to enable this feature. And also compared to many other data systems that are out there, the focus is on low latency queries, high QPS queries, and ability to do lots of writes on this database. So I think you guys at Pinterest you used to use a lot of Hadoop and Hive. I think maybe you still do. So if you want to compare it with those systems, the Rockset is different, or the technology behind Rockset is different, because we want to enable very quick insights on your most recent data set. So this is what traditionally the enterprise calls it as operational analytics. Very different from batch analytics or or real-time analytics. So, I mean, Hadoop mostly started the batch analytics revolution. Over time, people have moved more into real-time analytics using Kafka and Spark and ETL processes that are streaming data. What Rockset is doing is essentially trying to operationalize these analytics so that unlike Hadoop, where you cannot make hundreds of low latency queries, for example, right? Hadoop is mostly optimized for throughput. Hadoop is definitely not optimized for latency. So Rockset is optimized for low data latency and low query latency. So there are two different latencies that we measure. Data latency is if you produce an event right now, like let's say in Pinterest, a click stream, how quickly can you make that click be visible in your queries or your analytics engine? So that's the data latency, and how quickly can queries respond to you? That's the query latency. Also, typical examples I will give is things like, say, at Pinterest, I'm guessing just like Facebook, you have like spam detection, for example, right? So you need to find bad things right as and when it is produced, and you need to quarantine them, otherwise they just spread badly. So data latency is very important for those. Similarly, maybe for ad placement at Facebook, it is very important to get low data latency so that you can kind of look at the most recent thing that a person has done to show him some ads. In the enterprise world, there are many other use cases, but I can forget about that for a second. So Rockset architecture is different from other architectures because of three main reasons that I'm going to explain today. There are many other smaller things that I'm going to sideline for now, right? So one of them is smart schema SQL, which means that Rockset is exposed as a full SQL query engine, but you don't have to specify a schema up front. So unlike say systems where you put semi-structured data and then you associate a schema and then you start querying, in Rockset this is automatic, and I'm going to explain how the architecture enables this one. Also, compared to many other data platforms like say MapReduce type or even Spark, the whole big data ecosystem has been about parallelize my work and do small scans for the data set that you have, right? Let's say you have 100 terabytes of data. How can I get each worker to do 256 megs of processing or some few megs and do scan of them? Whereas in Rockset, the whole purpose is that I can actually do indexing on this data and give you fast queries rather than full scans. So I'm going to explain how the architecture enables that. And also Rockset is a serverless engine, which means that you can't really download it on your enterprise, or it's not something that you put it on your own machines. It's a software as a service. And I'm going to explain why being serverless is critical to be able to do converged indexing and smart schemas. I will take a pause after this picture, and then maybe I'll try to get more interactive. So there might be more questions bubbling in your head. And so let me finish this slide one more time, and then I'll go back to a few questions that you might have. So this is what is called the aggregator leaf-tailor architecture. This is the architecture that some of the inspiration for this architecture is things like Facebook newsfeed, where newsfeed was a backend, which is essentially an analytics system. It shows you the Facebook feed, but not everything. It has to do a relevance matching, it has to do sorting, it has to do aggregation and show you most relevant feeds from your friends, just like in Pinterest, right? So it's a relevance engine, it's an analytics engine, and this is what I mean by an operational analytics engine. The data latency is very low and the query latency is very low for these kind of Facebook feed application. So the way this the Rockset aggregator leaf-tailor architecture works is that let me use this one. So data is coming in streams. This could be click streams for us. It could be from data lakes, which is Hadoop, HBase, or S3, or some other data lakes. Or it could even be databases like, say, you have data in DynamoDB or you have data in MongoDB. Do you guys use Dynamo? Twitter is a big AWS user. Okay, anyway. So whatever data, Postgres databases, right? So people try to get data from all these data sources to be able to build your analytics. And so what happens is that there are a bunch of tailors that tail data automatically from these systems. This might be very similar to things how backend systems work at Pinterest as well. And then it goes to a set of leaf nodes. This is where the indexing happens. And then now you'd see that the writes kind of end here and the reads start from here. So we have very clearly tried to differentiate the portions of the architecture which is writes, which is doing writes, and the portion of the architecture which is doing reads. The tailors themselves, so the reason again this is a leaf tailor architecture is because there are three things that we want to scale independently. If there is more data coming in from the system, then we need more tailors because we need to be able to process them. If the total data size is very big, you need more leaf nodes because you need to store all this whatever data size it is. And then if your query volumes are very high, then you need more of this side. So you can essentially, it's a disaggregated architecture where you can, depending on your workload, you can scale each of these things independently of one another. They're not tied together. This is also traditionally very similar to the CQRS pattern where it's like, if you guys are familiar with database terminology in general or just programming, if you look for CQRS, you would see like 30 years of history on how CQRS systems are designed. So the writes are all here and the reads are all here. That's basically the uniqueness of the leaf tailor architecture as far as a database is concerned. Let me take I'm going to drill down into each of these boxes and explain how each one works, but any questions so far? Yeah.
The aggregator is stackable.
Oh, excellent question. Yeah. So this is basically the query engine that we have. So queries can come in from, so these types of applications are not dashboards or like periodic reports. I'm talking about, say, the ad placement application, for example, right? Or spam detection application. So what they do is that some of those applications need a lot of aggregation. So we have a 2-level aggregator right now. It can ideally be many levels, but in production when we have deployed, it's a 2-level aggregator, which means that aggregations happen locally on these, and then a final aggregation happens on this before results go out. And these mostly need CPU and RAM. This is what it is used for. The leaf nodes mostly need a lot of storage because it's going to be indexed. And the tailors also need a lot of CPU and transformation from, like, say, you have thrift data structures and you want to convert into Rockset format. So if you have protobufs and you want to convert into Rockset, if you have JSON, you want to convert to Rockset, those things all happen in the tailors. So that's why the 3 different things. So it's kind of looks similar in my mind, but the aggregators sometimes need a lot of memory because there is aggregation to be done, and aggregations go very fast if you have a lot of RAM. Making sense?
Yes.
Any other questions so far? Yeah, question?
So there is no pre-aggregation. All the data is stored.
Exactly, yeah. So there is no pre-aggregation. So some people also ask me, hey, is this very similar to a time series database? So time series database, what happens is that they are also kind of an operational analytics database because you can query whatever events just got produced. But the whole point is that it's only based on time. So indexing is only on time. Whereas in Rockset, it's a generalized version of as a time series database. You can index on every field, not just time. So you basically, the latencies that you get from a time series database is what Rockset can give you on the time index, as well as 500 other indexes that you might have in your data set. So let us talk about the first one, how the architecture enables smart schema SQL and what it essentially means. So this is a little bit heavyweight slide, but I'm going to go slowly. So let us talk about, so the data format that Rockset takes in are documents. These documents could be JSON, CSVs, or thrift documents, or protobufs, or something. In this diagram, I've just written JSON just because it's easy to explain. Let's say there is a JSON document coming in with these 3 fields, and then there's another document coming in with those 3 or 5 fields. You'd see that with the indexing engine supports nested documents. It also supports deeply nested arrays. So you can actually go and query every piece of the array that you might be in a very deeply nested JSON object. And what happens is that when you put in these documents, you don't really need to specify a schema for this collection. So you create a Rockset collection and you say, hey, deposit these documents. What the system internally does is that based on the document that's coming in, it will infer some of the schemas for you. So for example, here it will know that this document, the age is 31, is an integer, just because it's in JSON format. JSON, if there are no double quotes, that means it's an integer. But protobuf has its own type definition. Similarly here, age is a string. So unlike many other databases where if you put in these two documents, it will fail at the time of insertion because there's a field here which is integer and there's a field here which is a string. But Rockset doesn't. This is the whole point of making systems very user-friendly, is that you can deposit data as and when it's coming in. Is at the time of querying where you actually figure out what schema to use. So now we automatically deduce this schema saying that, hey, age is one occurrence of string, and then there's one occurrence of two of integer. So this is automatically deduced by the system, and because we index, and I'll explain how we index, this schema is kept up to date as and when single records appear in the system. So now, again, if you step back, the difference from a standard relational database is that a type is associated with a column in a database. So for us, it is not associated with the column. It is associated with each value inside the column. So every value inside the column that is stored has a type associated with it, which means that you can store multi-type values on the same column, and you don't have to do data cleaning when data is being piped into this database. So this database can take in raw, dirty data without you needing to clean it up and make sure that all fields are the same type and things like that. Is it making sense? Any questions?
So how do you resolve conflict? For example, if you have a null, if you have a string called null, right? And when you convert it to a type, do you want to convert it to a string or a null value?
Great question. So null is actually a type. So just like in standard SQL, null is actually the null type. So it's its own type. So when you make a query, so interesting question. So when you make a query here, and I have an example I'll show you. If you make a query saying that find me all records where age is greater than 20. And because in SQL, when you make this query, you can say that you know that he is referring to an integer. He or she is referring to an integer because he's saying greater than 20. So then it will match only this one. Whereas if you want to say that, hey, find me all records where age equal to some string, then it's going to do a type matching as well as value matching and find these records. So basically the type binding happens at query time rather than at data write time. Am I making sense now? Yeah. So now to do this is actually quite complicated because this, if you want to associate a type with every value in your column, your database might suffer a lot in the sense, this is the reason why people haven't done it before, right? And so take for example, for a relational database, you specify the schema up front, and then there are two records in the data, let's say, right? You store the schema in one place and you stored all the data in another place. And this data has to match exactly what is in the schema. Whereas in a schemaless, which is more like a JSON database, the type is essentially associated with every field and stored every field because every JSON could be a string or an integer. So for Rockset, what we do is we do something very simple. It's basically field interning. Have you anybody familiar with field interning? This is kind of store the fields in one place in very layman term, right? So take for example here there are two records. So instead of storing name John in two places, we just store some IDs and that thing gets stored in a different place. So essentially if you do field interning, we can reduce a lot of overhead compared to relational databases. But we still have a 30% overhead compared to relational databases. Yeah, this overhead could be essentially size overhead. So if you have a database which is 1 terabyte, this might be 1.3 terabytes if you store it in Rockset. Again, I'm just giving you a trade-off between what we are trying to do and why we are trying to do it. This field interning reduces the size needed, although we store the type with every value. But then as far as the query is concerned, for query execution, again, let's say in the strict schema system like a relational database, this whole column is strings and this whole column is integers, let's say, right? Whereas in a schemaless, it will be stored with this type is actually stored with every value inside this record. For these ones, let's say I just represented it as I, but basically it is an integer type. Whereas in Rockset, we use another technique called type hoisting. Have you heard about type hoisting in general? It's a recent thing that is quite popular in some of the recent research, where essentially for small blocks of data, If the type of those things are same, we hoist the type with the kind of the header of the data set automatically. It's a simple concept. We use type hoisting to again reduce the query execution time, because when there's a query which says that find me like integer, we want to do an integer comparison. If all of these are integers and it's an array in memory, we can actually use hardware instructions to do that very fast. Whereas you cannot really use hardware instructions to compare integers here because they're all stored along with the type. So there are one or two small techniques I wanted to show you. So again, if you search for type hoisting in Google, you'll find some papers on how other people have tried to do it in research. So smart schemas, we can come back to this later. And the interesting part that a lot of people ask me is that, hey, can you actually do indexing on large data sets? Because large data sets are costly. You have terabytes of data. Nobody has tried to index all this data. Is it really efficient? Can it actually be done in a cost optimal way? So that is a big question. The thing that we wanted to optimize is that in big data systems, queries are usually much slower than traditional Postgres or some relational database, just because everything is full scan and there's no index. So unless you build an index by hand. So for us, what we have tried to do is that we try to index all the fields in your document. So if you have 500 fields in your document, all these fields will be indexed. So in a traditional database, like say Postgres or RDS or whatever, probably use RDS, right, in AWS, okay, no? Okay, but all these relational databases, there is a command called create index on this column, right? Why do you think people create indices on any column in a database? Queries have become faster, yeah, on that column. But basically what we have done is that we have made this command obsolete using our architecture, which means that create index command doesn't exist anymore because we index everything by default. So there's a cost associated with it and there's a benefit associated with it, right? The benefit obviously is that all queries become very fast compared to traditional systems. And the cost is what I'm going to talk about mostly to tell you how actually we do this. Are you guys following me? Okay. So converged indexing. Is essentially able to build a lot of different types of indices at the same time, which can help different sets of queries. So I will explain each one of these. One by one. Oh, okay, let me tell you about this example. So let us talk about this document that's coming in. So our goal is to have a completely mutable database, which means that we want to index and store every field separately in the database. Somebody should be able to update only this field without having to delete the rest of the document. And also somebody should be able to find all these documents based on 5 different query patterns that I'm going to explain, right? So what we do is that we take these JSON kind of semi-structured documents and shred it to its individual key value to store it into an individual key value store. If you familiar with RocksDB or any other key value store, they're essentially the only thing that the storage engine supports are keys and values, right? There's no other abstraction to a key and to a key value store. So take, for example, this document. We index, here I show you how 3 ways we index, but actually we index even more. So let us talk about these 3. So the first 2 entries are very much like a traditional relational store, where we say that this is the record index. So the first byte of the key is R in this case. It's actually the letter R, right? And then the 0 is this document ID. So every document has a document ID, which is kind of its primary key. So that's the 0 is the document ID. And then we put this name here, this string, this column name, this is the field name. That's appended to the key, and the value is the value of the field. So now, if you want to scan through the documents, just like you want to do it in Postgres, you are going to use these values in the key value to execute that kind of query. On the other hand, we also have a columnar index inside it. So columnar index means that all the fields which have the same name, they all need to come together, because you're going to do a full scan on that column to find those values very quickly, right? We don't want to do 500 random reads to find all the values in one column from all your records. So the idea is to keep all the column values together in one place in memory or on storage. So the way we create that key is that we append the name, or we start off prefix it with the letter C, And then now you would see that name.0 and name.1, the document ID comes later and the column name comes first. So in a key value store, all keys are stored in a sorted order. I just forgot to mention this. This is kind of the default for most key value stores. So if you scan this, you are going to find all the documents one by one. All the records in the document will be close to one another. If you scan this column family, you are going to find all the column with name equal to name stored together. So this is basically becomes your equivalent like a column store that other databases might be having, right? And similarly here, it's an inverted index. This is very much like, so we take this document, we put the name and there's no value, which means that this is very useful to find point lookups. This is very much like, say, Elasticsearch or Lucene, which is what they do as something called inverted indices. Are you guys familiar with inverted index? Okay, so this is basically the inverted index we built. Now, if there's a query which says that find me a record where name is Dhruba, so that's going to do one lookup into this key value store and tell me whether this document exists or not. And the document ID is 1, it says here. So it takes only one query to find low selective or highly selective queries, and we use the inverted index. So we also have other indices that we haven't mentioned here, things like geo-index and currency index and other things. But the whole focus of Rockset is that it should be easy for somebody to use. And so we understand higher level things and we try to store things efficiently to be able to query them, use them at query time. So let's take this example.
Hello. So
Yeah.
I have a question that you mentioned it earlier, that all the columns are automatically indexes. So my question is, usually like when people build indexes, they don't build on single columns. The more important use cases is like the composite indexes. So how maybe you are handling this situation later in the slides, but I just want to raise it up.
No, that's a great question. Actually, this is a very common question asked to us whenever we try to present this. So thanks. So what we do is that, so by default, we build indices on all single family or all single name items in the incoming documents. But you can also set up a configuration saying that you want to build additional indexes on combination of these columns, but it is not automatic.
I see.
Does it answer your question?
Yep.
Yeah, okay, yeah.
Thank you.
Yeah, sure. So this is a very common question because most people try to build indices on like 3 of these columns together or few of these columns together. So take, for example, these 2 type of queries, right? So this is a query which says that find me where keyword is certain and local equal to English. I'm assuming that, let's say, there are only very few items that will be returned by this query. In that case, we can use the inverted index and mostly do like point lookups or galloping search to find out the answers to this request. Whereas if you want to do group by, order by, and count descending, and do a little bit of more aggregations on large data sets on only few columns in your record, then the system will automatically use the columnar index. Similarly, you can make geo queries, which will automatically use the geo index to be able to find things within a certain range. So this is what I mean by that. It makes it easy for the user to not have to figure out that what indexes to build and what indexes to use for every query. In the beginning, when we started Rockset, we debated a lot on whether to use SQL or whether to build a different kind of an API. And finally, we fixated on SQL just because it's easy to express very complicated algorithms using standard SQL. Any questions so far? Yeah, question? Let me take that one first. Yeah.
If you go to the previous slide, are the indices stored in the same data store, or are they actually separated, sharded separately?
Awesome, yeah. So I'm going to talk about the serverless part in a second. So logically, it's like the same data store. It's like one humongous table, let's say, with all the keys and values, but actually it's not in physical reality, it'll be different, and I'm going to explain that. 1 second, so there's one question from there.
Is this like an ACID database that you insert all these keys like in a single?
Awesome, yeah, great question. So I am going to roll back the slides for a second. So the question is this an ACID database? And I will go back to this one. So you would see that we have very clearly tried to build a database which is useful for operational analytics. So like take for example Postgres. People use Postgres for analytics, right? But there is always this concept of transactions and ACID. Here in an operational database, we have tried to eliminate the bottlenecks that you'll have if you have strict ACID semantics. So that's why you have separated out the writes and the reads. The only thing you can do is essentially put data into the database. The write pipeline is very different from the read pipeline. You see what I'm saying? So you can put, so if you're sending a high volume stream of writes and it's bursty traffic, sometimes that won't be visible in a query for maybe more than 2-3 seconds because they're still being indexed by the leaf nodes. Whereas in the time of streaming writes, we try to keep the latency between the reads and the writes very like in milliseconds essentially. The only thing that the system actually supports are atomic visibility of documents. So if you write a document with 10,000 fields, all those 10,000 fields will be visible in a query atomically, or none of them will be visible in a query. But it's basically atomic writes and not a distributed transaction that we are doing here. Did I answer your question? One more. Okay. So converge indexing. So the other challenge for converged indexing, and this is also related to some of the consistency questions that came up, is that typically if you use a binary tree, let's say you use InnoDB or MySQL or something, right? So when a document comes in with 500 fields, you need to go update 500 places in your data store to be able to update all the 500 fields. That's why people don't create an index on every column in your Postgres database. If you have a 500 fields and you create an index on each of the fields, every write to the database is going to update 500 records in your MySQL table or in your indexes. Yeah. So whereas the reason we use RocksDB is one of these reasons is that RocksDB essentially changes all the random writes into one sequential write on file. So what happens? Are you guys familiar with the RocksDB internal details a little bit? Yeah. Okay, maybe I'll just explain it for a few seconds. So in RocksDB, so this is not a Rockset invention, but this is mostly RocksDB that we're leveraging. So new keys come in, RocksDB writes it to a memory buffer. And let's say a document has 500 fields. All those fields will be in this memory buffer. And when it is time to flush it to the storage, it will flush it to one SSD file. Unlike a non-LSM engine where when it's time to flush it has to write to 500 places on the disk. So essentially it amortizes all the writes into one write on storage. So that's the reason why you use RocksDB, one of the primary reasons why you use RocksDB, and we can afford to index all the fields in a document without paying the price of random writes on storage. And then so the trade-off, this is the interesting part in my mind. So the space amplification. So if you use a very traditional columnar database like say Vertica, that's like kind of one of the first columnar databases that are out there. Our space amplification is larger, but we also are able to do very fast point lookups and as well as document lookups, just like MongoDB. So basically, it's very easy for somebody to use us because you can make document kind of queries like Mongo. You can do elastic kind of queries, inverted index using just like Elastic. And you can do columnar indexes just like warehouses like Redshift or Teradata or whatever is out there, which is very columnar oriented. Now, if we talk about a little bit about the serverless part of things, which is how we'll talk about how we do the sharding and what we do for kind of hosting large data sets in place. So the Rockset architecture is basically tuned for cloud because, like I said, we can scale 3 or 4 things independent of one another. And in the cloud, the interesting thing is that we can kind of, all types of hardware is available to use. Essentially, the earlier problems that we were facing as a database developer was that, hey, if you want to use a different piece of hardware, you have to wait for hardware to arrive. Whereas in the cloud, you can get all these things by just using a software API, which is why I'm going to explain what we did differently to be able to do this. So this is what I mean. This is what I kind of refer to is as serverless storage. So let me explain what is happening here. So this same picture that I showed in the aggregator leaf tailor architecture in a different fashion. So these are the aggregators, these are the leaves, right? So the leaves of all RocksDB inside it. So this data, when you write data to this system, it basically gets written to a distributed log, and then each of the leaves tail some portion of the distributed log and indexes it. Let me see if I have a better picture. Yeah. So instead of using RocksDB, we actually use another open source project called RocksDB Cloud. And then RocksDB Cloud, what it does is that it's basically a layer on top of RocksDB. It writes files local to the leaf machine, but it also writes those SSD files into cloud storage like S3, GCS, and Minio. So what it means is that if this machine dies, we don't lose any of its data because it's stored in RocksDB Cloud, which is automatically keeping a copy of all the SSD files in cloud storage. So this is the benefit of using RocksDB Cloud versus RocksDB, is that you don't have to build your own replication or you don't have to build your own data moving pipeline. We basically use cloud storage as a humongous shared storage that is available for us to use. So the APIs to RocksDB Cloud is exactly the same as RocksDB, so you don't have to change. The data formats are exactly the same, and you can have all these merge filters, compaction filters, everything just like RocksDB. The only advantage you get is that if this machine dies, you don't lose all your data because all your data is in S3, and you can create that same RocksDB Cloud instance on another machine. So this is what I mean by serverless storage, right? I used to do similar stuff back in like 10, 15 years back for something called SAN storage. There used to be like SAN storage, usually like highly connected or basically built. The SAN was a protocol built with hardware where you could actually access a shared device from many different nodes. But now it feels to me that S3 has become that. It's shared storage where I can access from many different machines. The other challenge is how do I scale out this? When there are more queries, I need to make more replicas of this storage, right? So RocksDB Cloud has a feature called, okay, before I explain that, so take for example here, these are the 3 leaf machines I had earlier. So data is being queried by the aggregators. Now I'm seeing that there is CPU contention on these machines, so I need more replicas of this data. So I want to create a leaf replica from, let's say, from this one. So what I'll do is that in RocksDB Cloud, there is this thing called zero copy clones. So you can actually clone an existing database because it's in S3 and create a replica of it here. And both of them are diverging from that point onwards. So it's kind of very quick to create a clone replica of RocksDB. This is what is exported by RocksDB Cloud. And the way it works is that this node is now going to clone that original RocksDB instance and make a new replica for himself. And he will start tailing all the new data that is coming in via the writes and start serving data from here. So now these two are kind of replicas of one another, and they have their own life, and they diverge from the point where you cloned one from the other. So this is another feature that we use, which lets us make replicas very quickly when needed. And also in the cloud world, it's very important for us to shut down hardware when we don't need it. That's the whole point of indexing. So that's the other reason why people haven't indexed earlier, I think, is because the cost of indexing is very high. So for us, our focus is how can we use as many resources when we need it, and then use as few resources when we don't need it. So this is why S3 is important for us, because S3 is really cheap storage. So the moment the replica doesn't need to be there because queries are slowing down, then you can kill this leaf and the data will only reside in S3, and there is very hardly any cost to pay when data is only in S3. So again, this is the other reason why indexing in my mind is possible now, just because of cloud elasticity. You don't need to provision 500 machines to do small workload, because you can get machines when you need it and you get rid of hardware when you don't need it. Question?
Is the distributed log something like Kafka? Or?
Yes, so the distributed log is very similar to Kafka, yes. We also played around with something called log device. You might have heard about it. And our code is written in such a way that we can plug in one distributed log from another if needed. Again, the reason there is a distributed log is because we want highly available writes. We never want writes to fail. But on the other hand, we don't want a bursty writes to affect query performance, which is why the distributed log is very important in my mind. The other interesting thing as far as the ALT architecture is concerned is that in the ALT architecture, the log is in front of the database and not behind the database. So most databases have a transaction log. So when you write to the database internally writes it to a log. And in my mind, if we are talking about an analytics database, that's not the right design. The right design is to have the log in front of the database and actually make it be there because you want to never lose a write. Like let's say you are doing click logs for Pinterest. You don't want to lose any of the data that people are clicking on. And it's good to store them, but then you don't want your query latencies to be affected by bursty write traffic, which is why this architecture is useful. Any questions so far? The time to create a new replica actually in real life takes us from 1 to 3 minutes, which is not great. We actually want to do it in a few seconds if possible. But there are some AWS limitations where time to spin up a node and like provision some hardware is still not very fast. But we are trying to decrease it by just having some other mechanisms of having like a small spare pool and other stuff that we can do. 1 second. Question.
What is the sharding based on a document ID? Or
Yeah, great question. So what is the sharding based on? Yeah, I forgot to mention this one. So like, let me tell you how, say, HBase or Cassandra does a sharding. So when a document comes in, you look at the primary key and it's range partition, right? Like, so if you are looking for a key or a primary index on HBase or Cassandra, you know which node this document is going to reside on. So in Rockset, we don't do that. What we do is basically hash partition, which means that we want to make sure that, so the system is optimized for low latency queries and not for high throughput queries, right? Very different in my mind. So low latency queries, what happens is that when the document comes in here, based on some hash of this document, we are going to store it in any of these leaves. So it's randomly spread. Okay, so when data comes in, you spray it out. Because when a query comes in, we want to make sure that we can run that part of the query on every node in parallel. So if you partition it by range, then the documents will be only on one node and all the CPU on that node will be busy when somebody is looking for a particular query. So for us, again, for ranking relevance and like this is how Facebook multi-feed also kind of work, is that when the query comes in, we want to spread out the query workload among all our nodes. So we spread documents randomly when they come in, and a query needs to hit all the nodes in parallel. This is basically like a search database. So like Google search is never slow, right? It's because of this. They don't go to a hash part to a partitioned range database to go find their data. You have to make sure that your query can hit all the 500 machines that you have to do it in parallel. So this is again the difference of the ALT architecture is that we are basically document sharded. This is what we call as doc sharding, whereas traditional databases mostly do something called term sharding. So you can kind of compare these two in research literature and see how they're different. Did I answer your question? Yeah, you had a question?
Yeah, so just wondering what's the 1 to 3 minutes latency? Is that loading the SST data into my memory or is this?
That's a great question. So what happens is that let's say each RocksDB instance has 100 gig of data, right? Again, I'm just taking a ballpark number. So the throughput from S3 to the leaf is quite high. So you can probably copy that 100 gigs in a few seconds, or let's say maybe 40 seconds, right? But the challenge is to provision a machine and load Linux onto it and then load all the drivers and then make sure its network is set up. So that's why this most of the time is over there. We also, all our software is containerized and run on Kubernetes. So Kubernetes also takes a little bit of time to be able to run the kubelet and talk to the Kubernetes master. Another question?
I guess was the containerized.
Yeah.
It's like how you guys containerized.
Yeah. So everything is running on Kubernetes from day one. So do you use Kubernetes here?
We're planning.
Planning to, yeah. So at Facebook, I never used Kubernetes. So that was another reason why this was all exciting. It was all new stuff. And I said, hey, I need to learn some of this. So yeah, I think that's all I have. Oh yeah, I have one more thing. So forget about this. So the focus again for us is that we want to do kind of smart schema SQL or schemaless SQL in our writes. And we also want to do converge indexing, and we want to do serverless, which means that person doesn't have to provision upfront how much data to use, how many machines to provision. It's automatically configured for you. So this is what I mean by the reason that we don't have to do all these three is why people can start using us very quickly and get analytics data at operational speeds very fast. So I leave this picture here and I'll take some more questions if you have. I'm done with the talk otherwise. Yeah, please go.
You can go back 2 slides. So the part I wasn't clear about was
This one?
Yeah, exactly. So you said the leaf consumes. So if you take the distributed log as a Kafka,
Yeah.
so then the leaf needs to decide what messages it wants to consume, right? But you said it's randomized and it's not sharded. So how do you handle that in the consumer side?
Yeah, okay, good question. So what happens is that, again, this is, let's assume that we are talking about one table in this whole thing instead of talking about multiple tables, right, or a collection. So once you create a Rockset table, let's say all these leaves are part of that table, yeah? So that distributed log has things like topics and partitions. If you're talking about Kafka in particular, like log device have a little bit different, but topics and partitions. So every document is hashed, and the hash could map to a certain topic or a topic plus partition. Am I making sense? So these leaves themselves decide which of those topics and partitions they are going to tail. And that's automatic dynamically, it could change because, again, the implementation is that we don't have any sharding. We have something called microsorting. So a table in Rockset terminology can have like thousands of microshards. And they get mapped into a combination of Kafka topic or log device topic plus partition number. And again, it's easy to move data around because this leaf, it can tail 2 partitions, but it can ignore some data that's coming in because he says, I'm not interested in this part of the data. So we have all that flexibility. Question?
Do you support the updates for records?
Yes.
Some record updates?
Yes, absolutely. So
how do you figure out the primary keys and or
great question. Yeah. So if you go back to that picture that I had, where if we have a JSON document, we index every field in the JSON document, and every field is stored as a separate key and a value, which means that you can update every field, individual field in a JSON document. You don't have to update the whole document. So it's a mutable database, unlike warehouses and other places where our Hive, it's not really mutable, right? No, you have like partitions appearing every 5 minutes or whatever. So here, every field is indexed and updatable by itself. So you can say that, hey, I'm going to update this field, and this is the document ID, and this is the only field I want to update. So we'll go and rewrite that RocksDB key, only that key. So we don't need to reindex the whole document. Do you guys use Elasticsearch in any of your backend stuff? That's another popular open source software. Any other question? Yeah, question?
I'm curious about how the optimizer works that chooses which index to use for the query.
Yeah, so we don't have a great write-up on the optimizer. But essentially what happens is that we collect statistics from each of the leaf nodes. So each of the leaf nodes actually gives you statistics about the, maybe I have one slide that I've hidden, let me see. Or maybe I'll go back to this one, yeah. So all these data that you see here, these are basically some forms of statistics, right? It tells you we actually have more than this. This is just the schema version of it. So now when a query comes in, the aggregator in the aggregator leaf tailor architecture, this guy is the guy, he is receiving all the queries first. There are again different ones for different queries. So he is going to figure out that he'll look at the metrics that are exported for the table. And we also support joins, by the way. So it's a little bit sometimes complicated to figure out whether a query will be highly selective or whether it will be low selectivity queries. But based on that, it will create an execution plan. And the execution plan goes to all these aggregators, and they don't need to figure out this aggregation plan itself. The guy who comes in decides this upfront, and then sends it to each of these aggregators. And then they store it so that you can also use it for future queries for those data sets. Yeah.
So the CBO fires at runtime, essentially, or is it doing that at index time?
For which?
For cost-based optimizers.
It's all at indexing time and query time. So indexing time, the only thing it does is basically give you histograms on the data set.
Yeah.
It doesn't really know how the queries will happen, right? So it is keeping a lot of metrics on how your data is looking like. I gave you a very sample example there about how many occurrences of which type, but it also has range partitioning inside. So now when a query comes in, it's at query time we have to apply those statistics and figure out what plan to run. So also we have looked at, say, the Presto optimizer. That's also pretty popular, I think. There are quite a few open source optimizers out there. But the difference for us is that we want to make sure that our optimization works because we have an indexing engine in the back, which is different from most other sources. So that's one differentiator. And the other differentiator is why we had to rewrite this cost optimizer is because we also want it to be cloud scalable, which means that in Presto, for example, right? Do you use Presto? So Presto is optimized to run on 50 machines. You set up 50 machines, and when a query comes in, Presto's job is to use whatever hardware it can and make your queries go fast. For us, our difference, when a query comes in, we want to use as many aggregators as possible. So it's very different from the Presto cost optimizer, for example, right? We want to use as many aggregators as possible, spin up more hardware, run the query, finish it quickly, and then shrunk your hardware. So this is why we cannot just take some open source code and rerun it ourselves. Those are the two reasons why the optimizer is different, or the execution engine is also different. Question? Great question. Yeah. So first of all, every Kafka message that you are tailing from the distributed log or any other log has the offset that is in there, right? That you are getting from the message. And so when we put it in a RocksDB database, let me go back to this picture. So if when you go back to the RocksDB database, the RocksDB database actually stores the last Kafka offset for each of the partitions or each log device offset that it has consumed, and store it so that if you restart, you know where to retail the log from, right? So it's atomically stored. And then every Kafka offset is basically a sequence number of the writes, right? So now when a query comes in, the query could say that, hey, I want to make sure that all my data is at this sequence number. And so you can fetch from all the leaves only data up to the sequence number that you have tailed from the log.
So one last question, because time is up.
Okay, yeah, last question, please. And I can hang out outside and you can ask me more questions later.
How does the Rockset for the time series queries?
Yeah.
Is timestamp also kind of type of field?
Yeah, no, great question. So how does Rockset handle time series queries? So time series is basically another index. So let's say every record in your document has a timestamp, right? So now we index all the fields. So obviously we are going to index that time field too. And our data is actually organized through some, so there are some higher level metadata that we keep inside each RocksDB instance, which gives us some range partitioning for each of these indexes that we build. So yeah, so time series database are actually, or time series type of queries are actually a first class citizen for Rockset. A lot of people do this because that's where to start from. Cool, yeah, thank you.
Okay.
I will hang around outside and I can answer any questions you have.
Thank you for coming.
Thank you, thanks a lot. It's a pleasure to be here.
Great talk.
Okay, thank you.
So you mostly focus on the right part.
I mostly focus on the right part because the read part, we have some slides that I don't have.
Right. Probably next time you can
Sure.
come to talk about read part.
Read part, yeah, no, absolutely.